My voice is gonna sound, I'm sorry my voice will sound so annoying, but please bear with me. So we're talking about these choiceless large cardinal axioms. So we have axioms that are so strong, we've had to drop AC. And the problem is that you really can't do anything without AC. I think I should just switch to a whisper. It's not gonna happen. I'm so sorry. Okay. So without AC, it's very hard to prove any theorems. For example, Giddick showed ZF is consistent with the statement that every cardinal is singular, except for omega. So if we do drop the axiom of choice, we need very different tools for developing the theory of large cardinals. And if you saw on the homework, the basic theory of large cardinals really heavily uses the axiom of choice. So the question is, how are you going to even begin to understand these choiceless large cardinals if you're forced into a background theory where you have almost nothing to work with? And so this problem was pointed out by Fudan. But it's really present in the literature, like up to 2010, almost no consequences of the choiceless cardinals were known at all. There was basically nothing. There are these reflection facts which typically don't use much choice anyway, but things like combinatorial consequences, everything was open. So one thing that Fudan was able to show in the early 2000s was that if you start with very strong hypotheses, like say, well, it's not even that strong, I guess. So depends on your perspective. So if there's a proper class of supercompact cardinals, and this is in the ZF context. Then there's a class forcing. I know I've mentioned this. Such that if G is V generic, then V of G satisfies AC. Well, ZFC, I should say, because in general, class forcing can destroy the axioms of ZF, but this one preserves ZF, preserves choice, and it preserves all the supercompacts. So this is actually sort of interesting and was unprecedented at the time, because typically the only way it was known how to show the consistency of large cardinals with the axiom of choice was by building inner models for large cardinals. So this showed a new technique for showing large cardinals were consistent with choice. So like if you start with a measurable cardinal, you can show that there's, and you're just working in ZF, you can show that there's actually a model of ZFC with a measurable cardinal by building the canonical model with one measurable, L of U. But for supercompacts, the canonical models are not known. And so it was unclear whether ZF plus these supercompact cardinals would actually be equiconsistent with ZFC. And really, you do need to formulate supercompact correctly to get this. So Wooden's theorem shows it is, but in a sort of unexpected way. So this technique allows you to actually, in the context of choiceless cardinals or large cardinal axioms, get some consequences of AC. So what you can do, well, let me first give you a very simple case of Wooden's theorem just to show you what's going on. So, well, let me leave it for later. So for example, Wooden was able to show this theorem if lambda is a singular limit supercompacts, then lambda plus is regular. So, okay, large cardinals, even in ZF, are going to give us some regular cardinals, the large cardinals themselves. But this shows that there are some interesting regular cardinals you can get from the large cardinals reflection properties that aren't obviously coming from just the critical point of some elementary embedding. So the regularity of successor cardinals is a sort of characteristic consequence of the axiom of choice, but you actually can get it by instead using supercompacts. And the way Wooden did these kinds of things was by, well, I'm not sure about this exact theorem, but the idea was you would use this forcing that he had defined to force enough choice in some extension of the universe to actually get these consequences. And then you would use absoluteness to show that the consequences actually already held in the ground model. So an application of this idea was due to Rafaela Carolo, who was a graduate student under Wooden, and she actually proved some consequences, some very striking consequences of the choiceless cardinals using this method. So she showed she used extremely strong principles. So she said she had something like, if delta is a limit of Berkeley cardinals, singular limit of Berkeley cardinals and extendables, then, well, by Wooden's theorem, delta plus is regular, but in fact, delta plus is measurable. This is quite strange because in the context of ZFC, measurable cardinals have to be limit cardinals, they have to be inaccessible cardinals. But here, because choice is failing so badly from the Berkeley cardinals, you actually get delta plus to be measurable. She did this by forcing enough choice that she could run things like Wooden's proof of the Kunin inconsistency theorem. But the escape clause was that you can't get these splittings of stationary sets. So she actually showed there is a stationary set S of ordinals of coph omega such that the club filter on S is an ultrafilter. Okay, so I want to intermittently apologize for my voice in case anyone arrived late and missed the first apology. So what I'm talking about today is how to get results like this, but just assuming a rank Berkeley cardinal. So first, let me motivate this with a question. So David Aspero asked if there is a J from V to V, elementary, and lambda is equal to kappa omega of J, are there regular cardinals above lambda? So could we be actually in the situation of Giddick's model above the kappa omega of this elementary embedding? So of course, this is in the context of not a C. So of course, there are some regular cardinals. Kappa 0 of J is regular, actually inaccessible, because it's the critical point of an elementary embedding. So is kappa 1 of J, kappa 2 of J. Here's lambda. So, but it's conceivable there could be no regular cardinals above lambda. It's not clear how to get them. So let me be a little more precise. So the combinatorial characterization of supercompact actually is weak in the context of ZF. So the normal fine ultrafilter characterization. The characterization I'll be interested in today is Magador's formulation. So recall, I think I said this last time, kappa is extendable. If for all beta greater than alpha, kappa, there is a beta prime even greater than beta, and an elementary embedding from V beta to V beta prime, critical point kappa, and pi of kappa bigger than beta. So Magador showed that there's an extendable, an analog of extendable that characterizes supercompact. So this is in ZFC. Kappa is supercompact. if the following holds. For all beta greater than kappa, there is a beta bar less than kappa and an elementary embedding pi from V beta bar to V beta with if you let kappa bar be the critical point of pi, then pi of kappa bar is equal to kappa. So got kappa, some beta above, we can find kappa bar and beta bar below, and an embedding from V beta bar to V beta, sending its critical point kappa bar to kappa. So it's sort of the inverse of what you had with extendable, where instead you'd find beta prime, kappa prime above beta and these embeddings. So the embeddings look the same. It's just where is which part is the domain and which part is the codomain that's changing. So anyway, in the context of ZF, I want to use Magador's formulation as the definition of supercompact. And the reason is supercompact can, it's just a common thing in ZF, definitions that were equivalent split apart, and certain ones that were useful in the ZFC context become very hard to use. And so that's why I want this formulation. So yeah, I wanted to say something about how Wooden's proof of that you can force ZFC works. So the basic idea, the first step in the proof, which leads to the whole thing, is this lemma. So if kappa is supercompact in the sense of Magador, so this is always in ZF. I'm working in ZF from now on, and I can't keep saying that because I can't say anything basically. But okay, so if kappa is supercompact, and P is the forcing collapses every element of V kappa to be countable. So not collapsing all of V kappa to be countable, but collapsing all of the V alphas for alpha less than kappa to be countable. So this is the analog of the Levy collapse. But normally in ZFC, you would only consider collapsing the ordinals less than kappa to be countable. But this is a very different partial order in ZF, because you can't immediately well order the elements of V kappa. Okay, so if you look at this partial order, then in VP, the axiom of dependent choices holds. So abbreviations are important. I'm learning. What's the proof? Well, hopefully you know what DC says. It says that every infinite tree uh, has an infinite path, or let's not say it that way. Uh, well, yeah, every tree of height omega has an infinite branch. But the formulation I'll use, which is simpler in this context, and it really makes it obvious why you want something like a supercompact, is DC is equivalent to the statement that every structure has accountable, in a finite language, let's say, has a accountable elementary substructure. So what you do is, okay, let G be generic for this collapsing partial order. And to show that in V of G, we have DC, suffices to show that if M in V of G is a structure, M has a countable elementary substructure. So what we'll do is take a name, M dot in V, for M, and let fix a beta large enough that M dot is in V beta, and using supercompactness, fix an elementary embedding pi from V beta bar to V beta with critical point pi equal to kappa bar, pi of kappa bar equal to kappa, and I want M dot to be in the range of pi. So this, it's not part of the Magador formulation, but you can arrange that any set is in the range of these embeddings. That will be an exercise. So now what you do is let, we can extend pi. So let G bar be equal to G intersected with the collapse to omega of V kappa bar. And it turns out that the pi, I'm just sketching this proof, but pi extends to a map from V beta bar, G bar, to V beta of G. And G bar is generic for this partial order. So what this gives us is we can let m bar be equal to, well, we have some point pi inverse of m dot, the preimage of this name under pi, because we put m dot in the range. So we can let m bar be the g bar interpretation of that, and we'll have this lift of pi. So we have this extension. I should have changed the name. So pi tilde of m bar is equal to m, and this means that pi tilde image of m bar is an elementary substructure of m, and in V of G, pi tilde image m bar is countable. So that gives us DC. So I guess I'll also put it on the exercises to prove this equivalence. It's really not so hard. Okay, Usuba noticed that you can actually get away with much less than a supercompact cardinal here to find something called a Lowenheim-Skolem cardinal. Well, it's something like every structure has an elementary substructure that's whose cardinality is in V kappa. So it's weaker than DC. It's something, it's an analog of dependent choice. It's an analog of the Lowenheim-Skolem theorem, the downwards Lowenheim-Skolem theorem. And it's an analog of, it's a weakening of supercompactness that actually just follows from ZFC. And he could use that to force choice as well. So to get a lot of these consequences of choice. So okay, this pretty much explains all the history of these simulations of AC in a choiceless context. So I want to talk about how you can just work in ZF if you have choiceless cardinals, say a J from V to V, or rank Berkeley cardinal. There's some, okay. So this involves a concept called an almost supercompact cardinal. So kappa is almost supercompact. If for all ordinals xi less than kappa and ordinals beta greater than kappa, there is an elementary embedding pi from, well, V beta bar. So there is beta bar less than kappa and an elementary embedding from V beta bar to V beta. I guess I should have said such that xi is less than beta bar and pi of xi is equal to xi. So it's a weakening of the of the Magador characterization of supercompact. And it turns out that it suffices for a lot of the applications of supercompact cardinals. So, for example, well, note if lambda is supercompact or limit of supercompacts, lambda is almost supercompact. And in fact, any limit of almost supercompacts is almost supercompact. It's pretty easy to see because we only demand these embeddings for each xi below. So if you're a limit of them, you get embeddings for each of the xi below the limit. And then we have this generalization of Wooden's theorem about the successor of a singular limit of supercompacts. So if lambda, well, let's just call it kappa. If kappa is almost supercompact, and singular, then kappa plus is regular. So how do you prove that? Well, let delta be the cofinality of kappa plus, and assume towards a contradiction that delta is less than kappa. Can't be equal to kappa because it has to be regular. So what do? Let pi be an elementary embedding from v beta bar to some, let's say, v kappa plus whatever, doesn't really matter. It would be enough to have an embedding to v kappa plus omega, but just to avoid coding, let's just do this, such that pi of delta is equal to delta. So so now fix a sequence beta, no, let's say gamma sub I for I less than delta in the range of pi and cofinal in kappa plus. So we can do this since by elementarity, my kappa plus is in the range of pi, and so there has to be a witness to its cofinality in the range of pi. for each, well, for each I in the range of pi, there must be some surjection f from kappa to gamma sub I in the range of pi. Again, this is because the range of pi is an elementary substructure of v kappa plus plus, and so it's closed under the existence of witnesses to any first order statement. So the fact that gamma sub I is less than kappa plus is a first order fact about gamma I. And gamma I is in the range of pi, so the existence of a surjection from kappa onto gamma I has to be witnessed by an element of the range of pi. Okay, so now let S be equal to the set of all f such that for some I in the range of pi, with I less than delta, f is a surjection from kappa onto gamma sub I. So S is this should be f is in the range of pi. So S is a fairly small set of surjections. The cardinality of S is less than the cardinality of V beta bar. In particular, S cannot surject onto kappa, let alone kappa plus. So this is true because S is a subset of the range of pi, and the range of pi is in one-to-one correspondence with V beta bar. And this fact that V beta bar doesn't surject onto kappa, it comes from the fact that kappa is almost almost super compact, which means that elements of V kappa can't surject onto kappa. It's another exercise. So now we take a function from S times kappa. We're going to define a function from S times kappa to kappa plus. So phi will do is it'll take in one of these functions f in S. So f is some surjection, and it'll take in some ordinal nu, which is less than kappa, and it'll just output f of nu. Okay, so notice phi is a surjection. The reason is that for cofinally many I, gamma I, well, I is in the range of pi, So gamma I is contained in the range of f for some f in S. And hence gamma sub I is contained in the range of phi, since phi contains the range of all of these f's. Okay. So therefore, so I want this to be a contradiction, and it is, because what happens is, look at for each alpha less than kappa, look at the range of, let A alpha be equal to set of all phi of f alphas for f in S. So this gives us the kappa plus is equal to the range of phi. So it's equal to the union for alpha less than kappa of A alpha. But each A alpha has cardinality strictly less than kappa. And that's because A alpha is the surjective image of S. And okay, a successor cardinal can be singular, but it can't be this singular. You can never have kappa plus be equal to the union of kappa many sets, all of size strictly less than kappa. The reason for that is that you could let f sub alpha from, well, it's a partial function from kappa to A alpha be the canonical enumeration. So since A alpha has cardinality less than kappa, its order type is strictly less than kappa. So we have a partial function that only acts on an ordinal less than kappa, but I don't want to say what that ordinal is, or maybe just to be less confusing, let me just say it goes from the order type of A alpha to A alpha, the canonical enumeration function. Okay, so now we have that if we look at the function f from kappa times kappa to kappa plus given by f of alpha comma nu, or whatever, what I want a new variable, zeta is equal to f sub alpha of zeta. I don't really know how to write a zeta because I'm not a number theorist. Then let's see, then f is a surjection because this gets A alpha is contained in the range of f, just because A alpha is the range of f sub alpha. But now we have a surjection from kappa times kappa onto kappa plus, and that's really, really bad. So that's a contradiction. Because, well, the proof that kappa times kappa has cardinality kappa can be done in ZF. If kappa is an ordinal, which it is. Okay. So let me just give you one more consequence of almost supercompactness. It's a little different. So if kappa is almost supercompact, then every, well, the set for any ordinal the set of eta complete, kappa complete ultrafilters on eta, I'll denote like this, can be well ordered. So why? Well, there are a few ways to prove this. So fix an ordinal nu greater than eta, and let pi be a map from v nu bar to v nu, with eta in the range of pi and everything. So we're trying to show that, and I guess I can put kappa in the range of pi. I want nu bar to be less than kappa. I don't even need to make it fix any ordinals below kappa to do this, for this result. So what you do is you show, it's enough to show that beta kappa bar of eta bar can be well ordered. Because then v nu bar will think this can be well ordered, and so v nu will think that this can be well ordered. Okay, so we'll well order this guy. So how do you well order beta kappa bar of eta bar? Okay, and I should really say, in case you're wondering, that these are the pre-images. So for any, you can fix an ultrafilter U in beta kappa bar of eta bar. Now look at pi image of U. This is a subset of pi of U, which is in beta kappa of eta. And the key is pi image of U has cardinality less than kappa. Well, to be clear, that's not quite true, but pi has cardinality less than or equal to v nu bar, and nu bar is less than kappa. And on your homework, maybe I'll ask you to show that this means that since pi of U is kappa complete, and this is a small collection of sets in pi of U, in fact, the intersection is not empty. So this isn't obvious because kappa complete only says that it's closed under less than kappa length intersections. And this is not a well-orderable family of sets. So you have to be careful. And I'm going to ask you to be careful instead of me. But you can see I'm very frail right now, so you have to forgive me. So what we'll do is let C sub u be the minimum element of the intersection of pi image of u. So let me just, to be clear, because this is a little bit like a crazy, only set theorists would write something like this. This means the minimum ordinal C that belongs to pi of A for every A in U. Okay? The interesting thing about C sub U is that along with pi, and you can use it to recover U. Because U is the set of all A contained in eta bar such that C sub U is in pi of A. Okay, so that tells you how to well order beta kappa bar of eta bar. Set U0 below U1 if C sub U0 is less than C sub U1. I mean, these are ordinals, so they're well ordered. And we have this injective function that sends U to C sub U. It's injective because we could recover U from C sub U in this fixed object pi. So that means that this is a well ordering of the ultrafilters on eta bar. So by elementarity, we get a well order of the ultrafilters on eta. So yeah, there's a lot you can do with these almost super compact cardinals. But it's not, it might seem like, well, okay, you changed from a super compact to an almost super compact. Did you really get anywhere? And under AC, you don't get anywhere because it's a fact that a cardinal kappa is almost super compact. So this is a ZFC fact. If and only if kappa is either super compact or a limit of super compacts. So, not so interesting. Of course, we can do anything we can do with a super compact cardinal if we assume a limit of super compact cardinals. But in ZF, the situation is totally different. Because in fact, well, let me remind you, lambda is rank Berkeley. If for all alpha less than lambda less than beta, there is a j from V beta to V beta with critical point in the region alpha lambda. The theorem, one theorem, I'll tell you a better theorem at some point, is that if there is a rank Berkeley cardinal, so for example, if there is a J from V to V, there is a proper class almost supercompact cardinals. So this is it's a very different situation because there doesn't have to be a single accessible cardinal above the rank Berkeley. So strongly inaccessible. There doesn't have to be a cardinal kappa such that V kappa is a model of second order ZF, sorry. Because this is just sort of by Gödel's incompleteness theorem. Because if you had a rank Berkeley cardinal with an inaccessible in that sense above, you would just get a model of rank Berkeley cardinal with ZF. So you can't prove that there is one in ZF. It's typical. So that means that the rank Berkeley cardinals that the almost supercompact cardinals that you get above the rank Berkeley cardinal don't have to be supercompact. They don't have to be limits of supercompacts. They're something different. So yeah, let me show you how you get those. The idea is kind of simple. So for each ordinal C, I want to show. So I'm assuming a rank Berkeley cardinal now, and I'm working in ZF. For each C, I'm going to show that there is an ordinal kappa such that for any beta greater than kappa C, there is a beta bar between C and kappa C, and an elementary embedding pi from V beta bar to V beta, such that pi of C is equal to C. And this is enough to get almost supercompact cardinals, because you just find if kappa is closed under the function C maps to kappa C, then kappa is almost supercompact. So once we know that this function is always defined, then it has to have lots of closure points because ZF holds. And so we get lots of almost supercompact cardinals. Okay, but as a corollary, we'll get an answer to Aspero's question. If lambda is rank Berkeley, well, if there is a rank Berkeley, there's a proper class of regular cardinals. Okay, so let me just prove this fact and then we'll take a break. I think I can do the whole lecture if you want. I don't know how painful it is to listen to my voice like this. So just let me know.
I think we can hear very clearly. No people for.
It's clear enough? Okay. So yeah, so let me prove this fact. So for each xi, you have this kappa xi, and then we'll take a break.
Okay.
So suppose towards a contradiction, kappa xi does not exist. So for each, so for nu less than, for I less than our rank Berkeley cardinal lambda, I want to define a sequence, a continuous sequence. So I'm taking limits at limit ordinals. Beta I of ordinals. Okay. So it's continuous, so you know what to do with the limit stages. What do you do at the successor stages? So let beta I plus 1 just be the minimum ordinal beta such that there is no beta bar less than beta sub I, and pi, well, I guess there's no beta bar between xi and beta sub I, and no admitting an elementary embedding pi from V beta bar to V beta that fixes xi. So the point is, we know that beta sub I, if we couldn't find such a beta, then beta sub I would actually have to be the ordinal kappa sub xi that we're looking for. So there has to be such a beta, and we can take the minimum one, right? If this beta doesn't exist, then that means that for all beta, there is a pi from some V beta bar up to V beta fixing xi, which is exactly the definition of kappa xi. So there must be such a beta I. So take that beta I guess I should also say I want beta to be at least as big as beta I. So let me just do this. So beta should be strictly bigger than beta I plus 1 has to get strictly bigger than beta I. Okay, so how does this help? So since kappa xi doesn't exist, the beta I sequence is defined for all I less than lambda. So let beta be equal to the supremum of the beta i's for I less than lambda. And let j from V beta to V beta be an elementary embedding such that J of C is equal to C. I think that's all I need. Well, and the critical point of J. Strictly less than lambda. So now we're going to get a contradiction. The point is, look at V sub, so let kappa be the critical point of J. And look at V sub J, V sub beta kappa 1 plus 1. Okay, so we know by the definition of beta kappa 1 plus 1 that there cannot be an ordinal beta bar less than beta kappa 1 admitting an elementary embedding pi from V beta bar to V beta kappa 1 plus 1 with pi of xi equal to xi. But we know also that beta kappa plus 1 strictly less than beta kappa 1, since kappa plus 1 is less than kappa 1. And J of V beta kappa plus 1 is equal to V beta kappa 1 plus 1. So if we let pi be equal to J restricted to V beta kappa plus 1, we get a contradiction. Because pi now fixes xi and it maps some V beta bar, namely V beta kappa plus 1, into V beta kappa 1 plus 1. It's exactly what we said couldn't happen. So that tells us that this sequence actually couldn't have been defined for all I less than lambda. It's a contradiction. So kappa xi does exist. Okay, so that gives us our almost strongly compacts, a proper class of them, just from the existence of a rank Berkeley cardinal. And it answers the Aspera question. Okay, so let's take a break.
Okay.
All right. So I want to describe a slightly more abstract approach to these simulations of choice. The idea is to actually prove some choice principles from the large cardinals, like almost supercompacts, and then things become a little easier. You don't have to work with the embeddings all over the place. You can just use some version of the axiom of choice. The version I'll be interested in is called well-ordered collection lemma, because it's basically the strongest thing I was able to get from an almost supercompact cardinal. So let's say that the well-ordered collection lemma or well-ordered collection holds at lambda if, well, there are two conditions. One is just that lambda is a fairly large ordinal. So this is for any alpha less than lambda, there's no surjection from V alpha onto lambda. Okay, that's sort of a technical requirement. Two is that if F is a family of non-empty sets, with the cardinality of F equal to lambda, then there is a V lambda indexed sequence so sequence A sub x for x in V lambda, such that every set in family F contains some A sub x for x in V lambda. Okay, so it's like the axiom of choice, except instead of choosing one element from each set, you get a fairly small collection of elements, and some of them, so each set contains at least one of them. So if instead of having x in V lambda here, we just had A sub x for x in lambda, then this would be equivalent to saying that there's a choice function on F. But instead, just demanding this V lambda index sequence is slightly weaker. So some consequences of the well-ordered collection lemma. Well, one, so assume a well-ordered collection at lambda. Then lambda plus is regular. And in fact, for any ordinal gamma greater than lambda, gamma plus has cofinality at least lambda plus. What else? And the club filter, if delta greater than lambda is regular, the club filter on delta is lambda plus complete. Yeah, so these are the basic consequences. There are things like every delta close, let's see, every family sets closed under lambda indexed intersections generates a lambda complete filter. Sorry, lambda plus complete filter. So lots of consequences of the axiom of choice. I mean, here it's worth these need to be family of, well, first they should be non-empty sets. And they should be sets of ordinals. Okay. So not such a big deal, but these things are sort of important for what I'll say later in the chat. Okay, so let's see. I want to prove the well-ordered collection lemma. So for which lambda? So if I shouldn't have said lambda because lambda was supposed to be the rank Berkeley cardinal. Sorry. So if kappa is a singular, almost super compact cardinal, then the well-ordered collection lemma, or then well-ordered collection holds for kappa. So there's a different version of well-ordered collection that works for regular, almost super compact cardinals as well. It's just instead you would say for any family F of non-empty sets, with cardinality less than kappa, there is some beta less than kappa and a V beta indexed family such that every element of F contains an element, contains one of the A sub X's. So this would imply that instead the closed unbounded filter on kappa would be kappa complete, and kappa plus would have cofinality at least kappa. So yeah, that's the only real major difference. So this is saying for families smaller than kappa, you get V beta for beta less than kappa indexed family of witnesses. Whereas for the singular ones, for families of size exactly the singular, you get a V lambda, V kappa for kappa equal to the singular indexed family of witnesses. So there are two different versions of the lemma, and I'm going to do the singular one. Okay, so fix your family, your favorite family of non-empty sets. And since it's well ordered, right, its size is exactly kappa, and kappa is well ordered. We can enumerate it as A sub xi for xi less than kappa. And we can assume, so we're going to prove by induction we'll prove sure. We'll prove by induction that for No, I need to arrange this slightly differently. So annoying not to have the axiom of choice. Okay, so instead, I want to prove by induction on alpha less than kappa that for any alpha indexed family, A sub c, c less than alpha, there is a V kappa indexed family um such that each A sub c contains some A sub x. Okay, so we can assume this is true for some fixed for all c less than alpha, and I need to prove it for alpha. So now fix your favorite family. Of A sub c's for c less than alpha. So they're non-empty sets. And I need to show you how to get the little a's. So the idea is we're going to use almost super compactness. So take beta large enough that A sub c, c less than alpha is in V beta, and take pi from, so we want a beta bar in between alpha and kappa, and a pi from V beta bar to V beta such that say A sub c, this family of sets, is in the range of pi. Okay, so what do you do now? You want note that, so note without loss of generality, let's assume that alpha is a limit ordinal. Alpha is a successor ordinal, so it's equal to alpha bar plus 1. It's very easy to finish the proof because all we need to do is take the family of witnesses for the A sub c's for c up to alpha bar, and then take any element of A alpha bar and call that whatever A sub x, and we put them all together, and that's going to be a family of witnesses for the whole sequence. So the successor case is really very easy, and I only need to deal with the case where alpha is a limit ordinal. Okay, so how do you deal with that? Well, for each c less than alpha with c in the range of pi, the range of pi has to actually also contain a family A sub x for x in V kappa of witnesses for the family A sub C, well, I can't say C anymore, A sub nu for nu less than C. So meaning that every element of this family contains one of these A sub x's. And the reason is by induction, such a family exists. And so by elementarity, there has to be such a family in the range of pi. Okay? But the point is that the set of xi for xi less than alpha they're cofinal in alpha, since alpha is a limit ordinal and pi of alpha is equal to alpha. So that means that for cofinally many xi below alpha, the range of pi contains one of these witnessing families. Okay, so now if you take all of the witnessing families and put them together, so for each, so we can find a function from the range of pi times v kappa to whatever, to the union of all of our sets A sub xi for xi less than alpha. It's given by, well, we take an element of the range of pi, and if that element happens to be a function of the form A sub x for x in v kappa, and we're given some x, we map that, or let's call it some w, we map that to A sub w. Okay, so this is, you can think of it as a ran pi times v kappa indexed family of elements, and it contains witnesses for all of these guys. Okay, so the point is that now ran pi times v kappa injects into v kappa. So we're done. The range of pi is pretty small, and so we've now produced a function that takes this v kappa indexed family and some element of v kappa, and it produces some witness. So that's our new family or new sequence of sets. And we know that since the range of pi was cofinal in alpha, and we had cofinally many good witnessing sequences for the initial segments of the A sub x's, we actually have now formed a witnessing family for the A sub x's. Okay, so that was a little quick. I think I will end early, not quite yet, so don't get too hopeful, just because I don't know how long my voice is actually going to last. Okay, so this gives us this well-ordered collection property for all the singular almost supercompact cardinals. But actually, you can get something that looks a lot nicer, even though it's really the same theorem. The point is, you can characterize the almost supercompact cardinals in terms of their reflection properties. So recall cardinal is sigma 2 reflecting. If V kappa is sigma 2 elementary in V. So every super compact, and in fact every strong cardinal, is sigma 2 reflecting, at least in ZFC. And this is because you can reformulate sigma 2 reflection by saying kappa is sigma 2 reflecting if for any x in V kappa and the least beta in any formula phi with one variable, the least beta in the ordinals such that V beta satisfies phi of x is less than kappa if beta exists at all. So a sigma 2 reflecting ordinal is just one where if there's some level of the cumulative hierarchy where something happens with this parameter x, it actually has to have already happened before kappa. So facts about the cumulative hierarchy get reflected below kappa. So this is only equivalent in ZFC, but sigma 2 reflecting does imply this property in general. The problem is getting sigma 2 reflection just from having V beta reflection. Okay, so in the context of ZF, I want to define kappa to be rank reflecting if for any ordinal alpha less than kappa, or let's call it C less than kappa, the least beta such that in any formula phi, I'm sorry, the least beta such that V beta satisfies phi with this ordinal parameter xi is less than kappa if it exists. Okay. So the theorem is rank, what did I call it here? I don't know. Rank reflection dichotomy? No. It's an almost super compact dichotomy. Is 1. So let lambda be the least rank Berkeley. So a cardinal kappa less than lambda is almost super compact if and only if kappa is either super compact or a limit of super compacts. So this is just the situation with ZFC, right? Almost super compactness is basically the same concept the supercompactness in ZFC. And the real reason is, remember, almost supercompactness tells you that you are able to fix these ordinals Xi, whereas supercompactness tells you something about what's going on with the critical point of an elementary embedding. But in the context of ZFC, if you have an elementary embedding from V alpha to V beta, and it fixes an ordinal Xi, then its critical point really basically has to be above Xi by the Kunin inconsistency. And that's the same thing that's going on in 1 here. So let's see. So supercompact cardinals, they're not characterized by this reflection property, because an ordinal that's sigma 2 reflecting could be singular. And ZFC or ZF alone proves that there are many sigma 2 reflecting cardinals. So it seems absurd to even try to characterize supercompactness with reflection properties like this. But it turns out that almost supercompactness above the least rank Berkeley cardinal is characterized in this way. So let's see, a cardinal kappa greater than or equal to lambda is almost supercompact if and only if it is rank reflecting. So in particular, every sigma 2 reflecting cardinal is almost supercompact above the least rank Berkeley, at least. So to me, this was surprising because I thought, okay, well, supercompactness is kind of like sigma 2 reflection if you demand that it's witnessed by elementary embeddings. But now we just have that this reflection property is automatically witnessed by elementary embeddings. And that's because the elementary embeddings are sort of coming from the rank Berkeley embeddings. If you look back at the proof of existence of almost supercompact cardinals from rank reflecting cardinals. So anyway, as a corollary, we get things like a theorem if kappa is rank reflecting above the least rank Berkeley, then any set of kappa complete ultrafilters on ordinals can be well ordered. And either kappa or kappa plus is regular. I mean, lots of these results that if you think about reflection in the context of ZF, you could never hope to have something like that. So it's a little strange. So I wanted to say just one last thing, and then I think I'll be done, about the club filter. So the fact that these choice principles that we're getting allow us to show this fact. If you have a rank reflecting cardinal greater than the least rank Berkeley, then for all regular cardinals, and we know there's at least one, by the way, because it's either kappa or kappa plus. But I guess since we have a rank Berkeley cardinal, we know there's a proper class of them. Then for all regular delta greater than or equal to kappa, the club filter on delta is kappa complete. But we also have this wooden proof of the Kunin inconsistency that seemed to show something like the club filter can't have a lot of disjoint stationary sets. So that's telling you something about how saturated the club filter is. So the theorem I want to prove is there is a partition of, so this is in the same context. So for any regular delta, so kappa is rank reflecting greater than the least rank Berkeley. Delta greater than or equal to kappa is regular. Then the set S delta omega of ordinals alpha less than delta of cofinality omega can be partitioned into sets S sub C, C less than gamma, such that the club filter restricted to each S sub C is an ultra filter. So what's the club filter restricted to the set S sub C? Well, you should have already seen it on the homework. It's just the set of A contained in delta such that there is a club C with C intersect S sub C contained in A. This is the club filter restricted to S sub C. But in particular, this implies, it's a corollary, that each let's see, the club filter so in the same context, either kappa or kappa plus is measurable. And what's interesting about this is all we said about kappa was it's rank reflecting. So there will be many rank reflecting cardinals of cofinality omega, and all of their successors have to be measurable because measurable cardinals are always regular. So this is saying that just from a rank Berkeley cardinal, we get a proper class of measurable successor cardinals. So it's sort of interesting. Getting measurable successors, really this is reminiscent of the axiom of determinacy. That's the only other context. Well, that and the theory of strong partition cardinals, the only context where you get successor cardinals with the strong that are measurable. The only set theoretic principles that are known to imply it. So now we have this from large cardinal axioms. I'm not actually sure whether there's any other theory that gives a proper class of successor of singular cardinals that are measurable. And especially they're measurable in a very special way, which is that they are, I think I mentioned this term, omega strongly measurable. there was this concept of omega strongly measurable in HOD, but these are omega strongly measurable in V. They're measurable by the club filter restricted to a subset of the Coph omega ordinals. Okay, so it's a pretty strong consequence of rank Berkeley. So how do you do it? Well, I hope I can. So the idea is, so this is the proof. So what am I trying to do? I just want to partition the, I want to partition S delta omega into fewer than lambda pieces. Such that the club filter such that the club filter F sub club restricted to each piece S is an ultrafilter. So let's see. How do you do it? Well, what we know from Wooden's proof of the Kunin inconsistency theorem is that there cannot be any partition S alpha for alpha less than lambda of S delta omega into lambda pieces, each of which is stationary. That comes right out of the proof of the Kunin inconsistency theorem, of Wooden's proof of the Kunin inconsistency that I did yesterday. Or actually, that was Tuesday. I'm losing track of time. So what we want to do instead is, so since we know that kappa is almost super compact, we can take a pi from V beta bar, well, let's say fixed beta greater than, much greater than delta. I don't know how much greater I'll need. Probably beta equal to delta plus 1 would work. And let's take an elementary embedding pi from V beta bar to V beta with beta bar less than kappa. Okay, so what am I going to do? And just look at all of the subsets. So I guess I should take delta in the range of pi. So look at all of the subsets of delta that are in the range of pi. So what we'll say is you can define an equivalence relation on delta itself by setting xi equivalent to xi0 is equivalent to xi1 if C0 and C1 belong to exactly the same subsets of pi of, of delta in the range of pi. So in other words, the set of all A contained in delta bar, where delta bar is equal to pi inverse of delta, such that C0 is in pi of A, should be equal to the set of all A contained in delta bar, such that C1 is in pi of A. So we have this equivalence relation on delta, so we can let S sub C be equal to all of the C primes less than delta, such that C prime is equivalent to C. And this is going to give us a partition of delta into these sets. Some of these sets might be equal to each other. I mean, they're just the equivalence classes of the partition. So let's call this thing U sub C0, right? It's all the A contained in delta bar, such that C0 is in pi of A. It might be familiar from the proof that you can well order the ultrafilters on delta bar. It's just a little bit of a different perspective on that proof. So for each C, we now have an ultrafilter on delta bar corresponding to C, and the same ultrafilter, it's like it classifies the equivalence relation slash sim that we're looking at, right? If C0 will be equivalent to C1 if and only if they have the same ultrafilter invariant. But anyway, the point is that this family of S sub C's, these subsets, for C less than delta, there can't be that many of them. So it's a well-ordered family, so I can talk about its cardinality as if that's just an ordinal. But its cardinality, it has to be less than kappa, because we have this injection sending S sub C to U sub C. It's well defined because U sub C only depends on the equivalence class of Xi. So this gives me an injection from the S sub C's into V beta bar. Much smaller than that, but we know that V beta bar can't surject onto kappa. And so any well-ordered family of sets that inject into V beta bar actually has to have cardinality strictly less than kappa. Okay, so we now partition delta into these sets S sub C for C less than delta, which we can now reindex by taking out all the repetitions. As a sequence T sub nu for nu less than gamma, where gamma is strictly less than kappa. Okay, so we have this sequence of T nus for nu less than gamma. and each T sub nu is an equivalence class. And the claim is that T nu cannot be okay, so the union of the T nus is equal to delta. Just because these are all the equivalence classes of some equivalence relation on delta. So their union is everything, because everything's in some equivalence class. And I claim that the T nus cannot be partitioned into disjoint stationary subsets. Okay, I have to leave that claim for another time because it's getting a little too complicated. I think I need an application of the well-ordered collection lemma that I tried to skip here. So this is left as an exercise to the lecturer. Otherwise, I'm I'm going to so I'll try to tell you about this better tomorrow, but otherwise, if I try to do it right now, I'll just go off the rails. Okay, so sorry about that. But the main point, okay, is that they can't be split. And now the point is, if we look at the ones that are actually stationary, then the union of the T nus such that T nu is a stationary subset actually of S delta omega contains all but a non-stationary subset of S delta omega. And the reason is that if you look at the non-stationary ones, well, that's the complement of this set in S delta omega. Well, this is the union of fewer than kappa, in fact, fewer than lambda many non-stationary sets. And therefore, its union is again non-stationary. And that's just using the fact that the club filter is kappa complete. So the intersection of fewer than kappa many clubs is club. And the union, this is just De Morgan's law, the union of fewer than kappa many non-stationary sets is non-stationary. Okay, so I think that's all I want to say. And yeah, I'm sorry that I forgot this part of the argument. I forgot to prepare this part. But anyway, so thank you, and I'll see you tomorrow. We'll be talking about combinatorial instantiations or aspects of the periodicity phenomenon for choiceless large cardinals. So I'm not sure I think I didn't talk about this on the first day, so let me just give you a preview of what I'll focus on. So for each alpha, you can let theta alpha be equal to the supremum of all ordinals eta, such that eta is the surjective image of V beta for some beta less than alpha. So this is a sequence of theta alphas is sort of an important characteristic of the sequence of V alphas. So we have theta omega is just equal to omega. Theta of omega plus 1 is equal to omega 1. In the context of AC, theta omega plus 2 is equal to the successor of the continuum. So in general, theta alpha plus 1 is going to be equal to Beth sub alpha plus almost Beth sub omega plus alpha plus. So for example, theta omega 1, omega plus 1 is equal to Beth sub omega, which is omega, wait, sorry, off on one or the other side. Theta omega plus alpha plus 1. Sorry. There's this annoying thing where the alephs are indexed so that aleph 0 is equal to omega, and the beths are indexed so that beth 0 is equal to omega, whereas the natural choice would have been to make aleph 0 equal to 0. This is what they should have done if Cantor had been alive back when I don't know, when everything started at 0. It would have been like this, and then aleph omega would be equal to omega. So omega would at least be an aleph fixed point, which it should be since it's supposed to be an inaccessible cardinal. But now this makes everything a little tiny bit different. So if you think about it, it's kind of annoying that aleph 0 is the first infinite cardinal instead of just being the first cardinal. Anyway, so we can state things like the GCH in the context of AC just says that for all alpha, theta omega plus alpha plus 1 is equal to theta omega plus alpha plus. Okay, but I want to look at what happens to the thetas in the choiceless context. So in the context of AD, I did mention this, theta omega plus 2, which is the supremum of the ordinals eta, such that there exists a surjective function from the reals onto eta. Theta omega plus 2 under AD is strong limit cardinal. That means that for any eta less than theta omega plus 2, you have the power set of eta does not surject onto theta omega plus 2. So theta omega plus 2 is the least ordinal such that the power set of omega doesn't surject onto it. But it turns out that it gets this much stronger property that the power set of no ordinal less than it surjects onto. Sort of surprising because remember I just said that under choice, theta omega plus 2 is just a successor cardinal, whereas a strong limit cardinal is a limit cardinal. It can't be a successor cardinal because it would be the surjective image of the power set of its predecessor. On the other hand, theta omega plus 3 is just equal to the successor of theta omega plus 2. So we got a tiny periodicity phenomenon, theta omega, which is a strong limit, theta omega plus 1, which is omega 1, which is not a strong limit, it's just the successor, theta omega. And then we have theta omega plus 2, it's a strong limit. We have theta omega plus 3, which is just the successor. So the theorem I'm going to talk about tomorrow is an extension of this periodicity property that takes hold much higher up. So it says, theorem, if kappa is a rank reflecting cardinal, kappa is greater than the least rank Berkeley, then for all even ordinals epsilon 1, theta sub epsilon is a strong limit cardinal. And 2, theta epsilon plus 1 is not a strong limit cardinal. In fact, it is the surjective image of the power of theta epsilon. So it's an open question, which could be fun for a graduate student. Is theta epsilon plus 1 just the successor of theta epsilon? So that's open. It should be true, but I don't know how to prove it. But anyway, we do get this periodicity phenomenon in the theta epsilons. This property, being a strong limit, holds exactly of the even ones. And it's replicating this determinacy theorem. And it's this property of cardinal arithmetic that you can establish from the choiceless large cardinals. You can never hope to do anything like this from the usual large cardinals because they're all consistent with GCH. This is a sort of very strong choiceless failure of GCH. Okay, and then one last comment. Even though I don't know how to do this, one thing I can show is that the set of regular cardinals in between theta epsilon and theta epsilon plus 1 has cardinality strictly less than the least rank Berkeley cardinal. So it's not the successor, but it's not too much bigger than theta epsilon in terms of the number of regular cardinals. Another open question, which could be much easier, is so if we knew that every successor cardinal was regular, then we could say, we could conclude from this that theta epsilon plus 1 is less than theta epsilon plus lambda, where lambda is the least rank Berkeley. But we don't know this, so you can ask, yeah, is theta epsilon plus 1 less than theta epsilon plus lambda? Another thing you can ask is, let's see, one last thing. Okay, it should be true that it should not be true that every successor cardinal is regular in this context. the context of the axiom of determinacy, many, one might even say most, successor cardinals are singular. So another open question, which could be fun, is there a singular successor cardinal? Assuming a rank Berkeley. The answer must be yes, but I don't know how to do it. And I think it would be a nice result, a nice analog of determinacy, if you could prove the existence of some successor cardinals that are singular. And maybe there's a lot more structure there that you could figure out. Okay, but I'm getting a little ahead of myself with the open questions. So we'll talk about this next time. I'm definitely not going to give a complete proof, but I'll give some of the key ideas behind this theorem. Okay, so thanks for bearing with me. Hopefully I'll have a little more of a voice tomorrow. And yeah, have a good evening.
Okay, thank you. Hope you could be better tomorrow.
Yeah, me too.
See you.